Hello and welcome to our last video on reaction types. Unless you're watching them in a different order, in which case, who knows what order this is. As far as double replacement goes, double replacement is going to involve starting with two ionic compounds. I'm going to use the front letters of the alphabet to represent my metals and the back letters of the alphabet to represent my nonmetals. So if I had AX, ionic compound AX, plus ionic compound BY, all that happens in double replacement, there are two ways to do this. You can swap your metals, and so in which case, I would end up with BX plus AY. I could swap my nonmetals, in which case I would end up with AY plus BX. Or I could take the outside letters, AY, plus the inside letters, BX. If you do the outie and the innie, just to make sure that your metal comes first. It should not be written as XB. The nonmetal never comes first. So I don't care exactly how you remember to form the products, as long as you remember it. So if any of those work for you, go for it. So a double replacement reaction that we're going to attempt to start is going to be, let's see, making up off the top of my head, these never go well. Let's do aluminum nitrate, if you need help with why I am writing the formulas, please see my earlier video on how to write formulas. So we'll do aluminum nitrate with sodium phosphate. No, let's do sodium hydroxide. I don't do hydroxide very much. And so I need to look at my chart. And I know that by looking at my chart, my nitrates are always going to be aqueous. And hydroxide is always solid unless it's bonded to ammonia or an alkali metal. The alkali metals are the group 1 metals. And so sodium is a group 1 metal. So that means even though hydroxide is usually solid, sodium is the exception. And so in that case, it's going to be aqueous. So now for my double replacement, my aluminum is now going to be with my hydroxide. My sodium is now going to be with my nitrate. And so with this, like I said earlier, nitrate is always going to be aqueous. So I'm going to write aqueous before I even do anything else. Hydroxide, we're going to use our chart, our solubility of ions chart. Solubility of ionic compounds, sorry. And we're going to look, and I see that hydroxide, like I said previously, hydroxide is usually solid unless it's in a compound with an alkali metal, calcium, strontium, and barium. Aluminum is none of those things, so it will be solid. In order for a double replacement reaction to occur, you need to have a precipitate form. The precipitate is the solid that forms when two aqueous compounds are mixed together. And so then, now that we have this, we need to balance. I have 3 hydroxide on my product side, so I need 3 hydroxide on my reactant side. That changes my sodium, and so now I need to put a 3 in front of my sodium. Now I have 3 sodium, I also have 3 nitrate, but looking at my reactant side, I have 3 nitrate, and my aluminums, I have 1 aluminum on each side, so I'm balanced. Now what we're going to do is, just like we did in our single replacement, I'm going to do the ionic equation. This is going to be my full ionic. So with my full ionic equation, anything that can be split into its ions is going to be split into its ions. And so that means anything that's aqueous. Aqueous, remember, means that it is soluble in water. It can break into its ions in water. And so the things that cannot break apart into their ions are anything that's not aqueous. And in this case, that's going to be my aluminum hydroxide. So when I do this, I'm going to have aluminum. It's aqueous, so it'll be Al plus 3 aqueous plus NO3. I'm going to keep the 3 with it, so that way it helps to keep things balanced. Aqueous, and it's a -1. Plus 3 sodium, aqueous, plus 1, plus 3 hydroxide, aqueous, -1, yields aluminum hydroxide. This is a solid. This is a crystal lattice because it's an ionic compound. So it stays together. That attraction between those two ions is strong enough that it will not dissociate, or it will not break into its ions in water. Plus 3 sodium, which is aqueous. Run out of room here. Plus NO3. Sorry, sodium was +1. NO3 is -1. And it is aqueous. Okay. So, just like we did in our single replacements, we're going to cross out anything that is the same on both sides of the reaction. So, I know that my aluminum hydroxide did not split apart into its ions. So there's no way that those ions are going to be on the other side for it to cross out with, because it's not in its ions. It's in a compound right now. So when I look at this, Al plus 3, I don't have an Al plus 3 on both sides because aluminum's involved in my compound. So it stays. Nitrate. I have 3 nitrate -1s. I have 3 nitrate, that was supposed to have 3 in front of it, 3 nitrate -1s. Sodium. I have 3 sodium plus 1s that are aqueous. I have 3 sodium plus 1s that are aqueous, so those cancel out. My hydroxide is in my formula, in my compound, so it will stay. The reason I put box around things was just so that way it's a little bit easier for you to track. It's to let you follow along in your books a little bit better. So now what I'm going to do is I'm going to do my net ionic equation. This is going to be a balanced net ionic equation. And so with this, I'm going to drop down everything that was boxed. So that's why I like to box things, because then it takes the thinking right out of it. I can just go into autopilot. So I'm going to copy everything down that I had up above boxed. I already did all the hard work, so now I don't have to think about it. All right, make sure I'm balanced. I have 3 hydroxide, I have 3 hydroxide, I have 1 aluminum, I have 1 aluminum. So I'm balanced at least. And so this is my net ionic equation, and this is as far as we take double replacement reactions. Now something to note is if you have a double replacement reaction that does not result in a solid. So for example, let's say that I reacted my aluminum nitrate above with sodium chloride. When these recombine, when these swap places, I'm now going to have sodium nitrate with aluminum chloride. Oops. Yes, AlCl3. And so I'll go through and balance everything really quick. So 3 chlorines, 3 chlorines, 3 sodiums, 3 nitrate, I'm balanced. But now when I go through and I do my state scripts, nitrate is always aqueous, no exceptions. So that means this will be aqueous. Chlorine, if you look at chlorine is usually aqueous unless it's in a compound with silver, mercury, or lead. Aluminum is not silver, mercury, or lead. And so in this case, it would be aqueous. If we have all aqueous compounds, then there is no reaction. Because for a reaction to happen, there has to be a precipitate. There's no precipitate, there's no solids. And so when this is broken down into its ions, I'm going to skip some steps here just for sake of time. I'm not going to worry about the whole being balanced bit. So just in the sake of time, I'm not doing the balancing. And I'm not writing the state scripts. Everything is aqueous because everything is in its ion form. I feel so bad that I'm not properly writing the subscripts and balanced charges and all that stuff, but that's okay. Living dangerously. And so by doing this, if everything is aqueous, everything breaks into its ions. And so then everything ends up canceling out. And so we have no reaction. You don't have to do down to this point. Just know that if you have all aqueous, if there's not a precipitate that forms, then it's going to be no reaction. Don't waste your time. Stop there. I hope this video helped you. If it did, make sure you click the like button. That just lets me know that it's worth my time to make these. Otherwise, I hope you have an awesome rest of your day.